4 kilo ohms, right?
Yes.
Okay. Now, so your base circuit would effectively be this one, right? We could use this Thevenin equivalent in that. Now, what about this base current? How would you find the base current for this NPN transistor? We can obviously assume that your VBE is 0.7 volt. Okay. Assuming that is the case, what is your VE? VE is VB minus 0.7. Right. And your VB, what's that? VTH minus IBRTH. Correct? And also your IE, what's that? It would be beta plus 1 times IB. Right? Beta is given. I'm assuming you all know this. Even if not, we did derive this one in the last session from the basic equation. So I'm not going to do that again in this one. This would be 101 times IB. Okay. And now from this 0.5 kilo ohm emitter resistor, right? So should be the VE, right? I need to determine this one. I already know the current that's flowing, right? That's this. So then your VE, that would be -5 plus this drop, right? Across this. How much would that drop be? IE times 0.5 kilo ohm. Is it fine? Is this much fine? Should I proceed? All right. So now, if you solve this one, right, since IE is in terms of IB, VE is in terms of IB, right? This and this we already know. So this is actually an equation with only one unknown, right? IB, right? And if you solve that, what is the value of the IB that you get? I'll directly write that, okay? The IB comes about as 13.95 microns, right? And once we know IB, what's our IC? Right, because this is all one goal, right? We have to compute IC. What is IC? Given IB,
Beta into IB.
Yeah, and how much is that?
139.5 kilo ampere.
Kilo ampere.
Sorry, micro ampere.
Micro? 1?
What is written there? 13.95 IB?
This is
Microampere.
micro. This is micro.
Yes, then IC will be 1395
1395
microampere.
microamp. Right. I can write that as this, right? Milliamps. Okay. So approximately, you can approximate this as 1.4 milliamps, right? So we discard these two options, right? We are left with these two, right? Now we need to find this VC, right? How do you calculate VC? How much is emitter current? How much is
IC
emitter
plus
current?
IC plus IB.
Yeah, and how much is that? If you do the maths, it comes about as 1.409 milliamps. Okay, and how much is V? V would be 5 minus
Minus 4.2.
5 minus, yeah, IC times 5 kilo, right? Interested in this one, right? VC. So that's why I'm trying to express it in terms of that. So now this one would be, sorry, this one is V, right? VC. So V would be 5 minus what? And this would be minus 5 times minus 5 plus 1.409 milliamps times 0.4 kilo. Correct? So your VE, that would be approximately minus 4.295 volts. Right. And how much is your collector voltage? That is 5 minus IC times 5 kilo. Right? And that is 5 minus 1.395 milli times 5 kilo. Right? That is approximately how much? Minus 1.98 volt. Okay. So how much is your VC? Yes. Means simply subtraction of the two, right? You know this, you know this. VCE would be how much? Approximately 2.32 volt.
2.3.
Yeah, 2.32 volt. So that is our Q-cent point. You can take that approximately as 2.3. So your correct answer would be this one, option B. Is it? Yeah, right. So now next question. In the circuit of the figure below, your Zener voltage is Vz equal to 5 volt and beta equal to 100. The value of ICQ and VCEQ are, again, I'll wait for a couple of minutes. Can attempt this one. I mean, we need to first determine what does this Zener diode fix, right? So what is base voltage here? Your emitter is grounded, right? Is it? Right.
Yes.
So how much should the base voltage be? Because
Maybe
VBE is 0.7, right? So how much is VB?
0.7.
Yeah. So
0.7.
VB would be 0.7, yes. Now, then we will use the Zener voltage, right? Since Zener is connected between your collector and base, right? So VC minus VB would be VZ, right? Is it? Yes, right? Now, what would VC be equal to then? VZ plus VB, right? So your VC would be
5.7.
5.7 volt, right? VB we did. Now, so then VCE would be how much? What about VCE? How much is that?
5.7.
5.7. That is same as VC. This is 5.7 volt. So we can, in fact, then compute the current through the 500 ohm resistor, right? How much would that be? Since we know this one right now. VC we know, this we know, this we know. We can find the current. Am I right? How much would that current be? It would be 12 minus 5.7 divided by 500. That would be 6.3 divided by 500. And that is 12.6 milliamps. Right? I mean, although this is not exactly what IC is, right? IC would be this plus this, right? But this much we know. Now, what about the other one? At the collector node, the resistor current would supply IC as well as the Zener current, right? In fact, it's the other way around, right? In fact, this splits up. This is this plus this, right? So if I were to write in terms of equations, IR would be split into IC plus IB, right? And then how much is my IC? Beta times IB, right? So, and my beta is 100. So this would be 101 times IB. Is it? IR I already know. I can compute IB. How much is IB? Do the maths, it comes about as 0.12475 milliamps. Okay. So this is my what? IB. The quiescent point that I was supposed to compute is IC and VCE. My IC. What will be my IC? IC would be 100 times IB. That would be 12.475 milliamps, right? And VC I already have, right, 5.7 volt. So which answer is correct? Option B, right? Let's move on to the next one. Is this fine so far? Any questions? Okay,
No, sir.
okay. So now this one, right? In this current mirror circuit, the transfer parameters are, again, I mean, VB you can take as 0.7 and beta you can take as 50, right? The early voltage is infinite. Assume the transistor are matched, right? So what is the output current I naught? That would be in fact the collector current on this one, right? That is your I naught. I'll wait for a couple of minutes again. So now this is a basic BJT current mirror, right? But because your beta is finite, your this 1 milliamp reference current, it must supply base currents of both the transistors, right? So since you are having matched transistors and they have the same VBE, right, equal to 0.7 volt. So what we can write is as follows. IC1 is IC2, right, since they are matched, and that is equal to I naught. Is this correct? And for each of the transistors, your IB, right, IB would be same in both. And your that IB, that would be IC by beta, right? If you apply KCL at that common base collector node, right, this one, what do you get? That IREF, a reference current, IREF is equal to IC1, collector current flowing in the first transistor, plus IB1 and plus IB2, right? See, this is IB1, this is IB2. Their sum is this much. And then IC1 is this, right? That's why your IREF is this. Is this clear? Yes, no?
Yes.
Okay. Then let's put in the values. So your 1 milliamp would be equal to how much? Would be equal to IC plus, what is IB1? IC by 50, because beta is 50, right? IC by 50, right? So your 1 milliamp is equal to IC times 1 plus 2 by 50, correct? That IC would be equal to 1 milliamp whole divided by 1.04, right? Which is how much? 0.9615 milliamp, right? And that is in fact your I naught, right? That is your I naught. I naught is equal to IC, which would be equal to, I mean, the closest option is 962 microamps. Done? Correct? In fact,
Yes, sir.
yeah, in fact, the useful formula that you could note for this two transistor matched current mirror that you could note would be this one, right? Your I naught would be equal to IREF whole divided by 1 plus 2 by beta. I mean, this is assuming the transistors are matched, right? Your this IREF is this one, right? And your beta is a beta of any of the transistors. You put in the values, you'd get directly this one. But I mean, it's good that we know how it comes about, right? One thing to note is that you have neglected the early effect in this. Okay, since your early voltage is infinite, make sure you remember that assumption while you're using this formula if you plan to do so. So we are done with this. Let's move on to the next one. Okay, now this one. Consider the circuit. The transistor parameters that are given is, again, I mean, early voltage is infinite and beta is 120. So the hybrid pi parameter values of GM, R pi, and R naught are, what are those three values? Let me wait a couple of minutes. Yeah, so what should we do? First of all, we'll find the DC operating current, right? And for the DC analysis, the small signal source voltage Vs, right? Your Vs, that is set to 0, right? You set that to 0, then effectively what you'll be computing would be the DC operating point. So what would you get? Since we are assuming VBE as 0.7, right? BE would be 0.7. Okay, 0.7 is this one, right? I mean, since emitter is grounded, so this one would be 0.7. So we know this voltage, we can compute what? What can we compute? We can compute many things in fact. I know this node voltage as well. I know this voltage as well. So this is 0.7, right? So let me first find out this current. IB. What is that? How much would that be? That would simply be 2 minus what? Divided by 250 kilo. 2 minus. Are you all with me in this question? Or should I repeat it?
0.7. 2 minus
Yeah.
0.7.
Yeah. Respond as fast as possible. I mean, that would help to finish this question even faster. So if you calculate this, I mean, somebody should have scientific calculator handy and should only be doing calculations. I mean, you all can work coordinatively, right? So how much is IB? It is 5.2 microns, okay? But now, the beta that you are given is 120. Yeah, beta is given as 120. So since I know beta, I can compute IC because I already know IB. IC is what? Beta times IB. And if you multiply this by 120, you will get 624 microns. Right? Now, so I know IB, I know IC. Right? Yeah. Now, to check if the transistor is active, what is the collector voltage VC? See, now I already know this. This IC I know. This I know. I can compute this V0, that would be my VC. Right? What is VC? VC would be 5 minus IC times 4 kilo. Correct. That is 5 minus 0.624 milli times 4 kilo. Correct. This kilo and milli would go. Right. VC that you get is 2.504 volt. Now, how do you check if your transistor is indeed in the forward active region? Is you compare VC with VB, right? And that is greater, right? VC is greater than VB, right? Because our VB is 0.7 volt. We already compared that, right? Since V is grounded. So what we can deduce is the transistor is in forward active region. Our transistor is in forward active region. Okay, now let's compute GM. For the hybrid pi model, what is GM equal to? Would have done the formulas, right? For hybrid pi model, you write GM as
IC by
IC,
VT.
correct, IC by VT. And how much is that then? Siemens, in terms of Siemens SI unit, or let's say let's report it in milliamps per volt. It should be 24, right? In fact, all the options have this particular value, right? So what I did was I divided this one by this one. Now, R pi. What about R pi? R pi is equal to the hybrid pi model. What is R pi equal to? It's equal to beta by GM, right? And your R pi, if you plug in the values, right, use beta 120 and use GM 24 milliamps per volt, your R pi would be 5 kilo ohm. And the last one, RO, right? What is RO equal to? Since your early voltage is given as infinite, right? So your RO would be infinite as well, right? Because RO is equal to what? VA by IC, right? Which would be infinity, right? So we are done with all of them. And what is the correct option? Correct option is D, right? Uh, Please make sure you remember the relations because I mean you are supposed to remember them while solving these type of questions. Okay, let's move on to the next one then. Does anyone have any doubt in this one? No, right? Let me proceed then. Now this one, question 11. I'll wait again for a couple of minutes and then probably start solving it myself. Yeah, so you consider this common base amplifier. GM is given, RO is given. You need to find the Thevenin equivalent that is faced by the RL, right? So basically you need to compute two things, Thevenin voltage VTH and Thevenin equivalent resistance RTH, right? Again, if you uh, no, just a second, let me share the screen, but for some reason it's perfect. Can you see the screen?
Yes, sir.
Okay. So how should we proceed on this one? How do we compute VTH and RTH on this? Yes, there are around 8 students in the meeting. Anyone? Obviously, I mean, our VTH would come in terms of VI, right? What is VTH by definition? I mean, given a network, how do you compute VTH? Thevenin voltage. We actually already did that in the first question that we solved today. See, to find VTH, what you do is you remove RL so that your output is open circuited, right? And the voltage that's appearing across output terminals, that is your Thevenin voltage, right? So what I can say then is okay. So we are given two things, right? We are given GM, this is 2 millisiemens, and RO, that is 250 kilo. Right. What would be V pi? V pi would be how much? V pi would be V B minus VE, right? And VB is, I mean, your base is at AC ground, right? So it's effectively minus VE, right? And at the open circuit collector, your KCL would give VO minus VE, right? And that is equal to GMV. So if you rearrange this one, your VO, that would be equal to VE whole, I mean, multiply by V1 plus GMR, right? That's if you rearrange this one. And then since your output is open and your base current effects are anyway neglected, right? So essentially no net current is drawn through this one, this 270 source resistance. So your VE is essentially VI, right? So what we can write is our Thevenin voltage VTH, that is equal to, I need to write this approximate sign, right? That's 1 plus GM RO times VI, right? So now GM RO, how much is GM RO? We are given them. I mean, those quantities have been given, right? That product GM RO, that's 500. You can check, right? Multiply both, you will get 500. Now, so how much is VTH then? Thevenin voltage? That would be 501 times VI, correct? So the nearest option that matches it is this one, right? 498 VI, right? I mean, it could perhaps the slight difference uh, that could perhaps be due to the approximations that have been used in the result, or I should say while evaluating the result. But yeah, option D is correct for the first one. And for the Thevenin resistance, what do? To turn off the independent source VI. Okay. Once you turn off VI, an ideal voltage source, what does happen? what happens to the ideal voltage source? It becomes a short circuit, right? So your emitter sees RS, this one. That's it. RS equal to 270 ohm. And that's going to the ground, right? It will be this one. So if you apply Vx at the output, right? For a transistor with emitter degeneration RS, the resistance that is looking into the collector would be your this RTH, right? How much is RTH then? Your RTH would be RO plus RS plus GM RO capital R, right? Or I could equivalently say this would be GM. I mean, I can take this RO common, right, from this and this. What will I be left with? RO 1 plus GMRS plus RS, right? And GMRS is how much? GMRS is 0.54, correct? Yeah, GMRS would be 0.54. So how much would RTH then be? RTH would be 384 kilo, right? So for this one, A, and for part A of the question, it was option B. So yeah, I mean, the relation that was important to remember in this one is that for a common base stage with a emitter resistance, your R out, right, that is given by RO plus 1, RO times 1 plus GMRS plus RS. Okay, which shows why your 270 ohm resistor, it raises the output resistance from 250 kilo ohm to roughly how much? 384 kilo, right? So we are done with this one. Any doubts? If not, then let's move on to the next one. So all transistors in this, what should I say, an output mirror in this figure, they are matched with a finite gain beta, right? And your early voltage VA is again infinity. So the expression for each load current would be how much? So this one would be the last problem that we do today. Let's do it well. So you need to find the expression for each load current, right? See, the important feature is uh, your this transistor, right? This extra transistor, QS, I should say, right? It supplies the base currents of your N output transistors and the reference transistor, this QR, right? It supplies base current to all of them, right? So what I could say is, if this is my V plus, I mean, let me draw the current flow picture, right? Here, V plus, right? This is your R1. This is what your IRIF, right? This is the base of your QS transistor, right? Which is at what? This is base of your QS transistor, and this is VCE of your reference transistor, right? And then this one applies the emitter current from this transistor, gets into what? We'll have a common base node, right? And all of your transistors, Q1, Q2, so on up to Qn, okay, they are fed by that current, okay? So now, because your QR, Q1, and so on up to Qn, they are matched, right? We'll assume that they are matched. In fact, they are matched, right, with a finite gain beta. So they'll have same VBE, right? So, and your ICR, right, the collector current in your reference transistor would be same as this IC1, IC2, so on up to ICO, right? And for each of these transistors, your IB would be how much? I naught by beta, right? There are your N output transistors, and you have a reference transistor as well, QR. So we'll have total of how many base currents? We'll have N plus 1 base currents that must be supplied, right? So what I can write is IE that must be supplied would be equal to N plus 1 times what? Their base current, right? Which is IO by beta. So for this source transistor, right? This is the source transistor QS. For the source transistor, this IE, yeah, any issue? Okay, brilliant. IES would be equal to your beta plus 1 times IBS, correct? And so therefore your this, yeah, this much is fine, right? This I'm relating my emitter current of my source transistor to the base current of my source transistor, right? So if I substitute this one, can use this one over here, right? I'll have what? I'll following. I'll have IBS, base current of the source transistor would be IES by beta plus 1. But what is IES? That is N plus 1 by beta times beta plus 1 times IO, right? And at reference node, your IREF divides into the collector current of your QR and the base current of your QS, right? This is where IREF is getting splitted. So your IREF would be equal to collector current of your as reference transistor plus your base current of your source transistor, right? So what is IREF? That would be equal to ICR, collector current of your reference transistor would be IO plus base we have already computed, right, for the source transistor in terms of IO. That is, should write it somewhere else, right? Plus n plus 1 by beta times beta plus 1 times what? IO, right? So if you take IO common, what do you get? Get 1 plus n plus 1 by beta times beta plus 1. Right, that is your IREF. Let me utilize the next page. So what is I naught then? In terms of IREF, simply divide by this ratio, right? Could be 1 plus n plus 1 by beta times beta plus 1. That's your answer, right? Option A is correct, right? Is this clear? Anyone having doubt at any point in this question or in this session in general? So for first 10 odd minutes, or I guess 10 to 15 minutes, I forgot to record the session, so that part is missing. The rest of things have been included. In fact, I guess I started the recording from question 1 itself. Initial portion of part 1 is missing, rest everything is recorded. Does anyone have any doubt? If not, then I would end this session here. No?
No, sir.
Okay. Yeah, so I guess who whosoever doesn't have any question can leave. I'll still wait for 5 minutes in case somebody comes up with a question.
Sir, please upload the links for the previous
Okay, okay.
problem solving sessions.
Sure. I'll do that. I'll
Okay, sir.
immediately post 2 of them. I mean, I already sent you the chat. I'm not sure
Okay.
how fast NPTEL team would give you that, but just a second. Were you able to access that channel? I mean, I had shared the link in the chat, right?
Sir, where you will be shared?
Just a second. Check chat. I'll share it soon there.
Sir, can you update in the NAPTEL where we are doing the NAPTEL course?
Yeah.
There is a problem solving sessions. Can you
Yeah,
upload their link?
I'll do there as well. I mean, anyway, I mean, you'll be having a separate playlist on this channel as well, and those links are the ones that would go there. Okay. I mean, I'll do it by today. Give me one day.
Okay, sir. Thank you.
Okay. Does anyone else have any query apart from sharing the recorded links? Any feedback on today's session or the session that we conducted before? You can also give me feedback on the pace at which I'm moving. Is it fast? Is it slow? I'll try to take that into consideration in the next session then. You can type in the chat as well if you have any feedback, or you can mail me as well separately. Okay, then stop in the recording. Okay.